Hello, ladies and gentlemen. So now we're going to do this problem. Let's read it together, first and foremost, okay? So suppose Bob is going to fence his rectangular farm, okay? Its sides are oriented with the cardinal directions, and the north-south ones cost $5 per foot to fence, while the east-west ones cost $10 per foot to fence. If the area of the plot is 144 square feet, what dimensions minimize the cost? Okay, so of course here we're in the area of make believe. Obviously, if Bob has a farm, he already has it, so it's not up to him to decide what the dimension should be, given these cost conditions. But here we're asking the questions: if it was up to him, and if he did want to pick the dimensions to minimize the cost, and assuming that this is the cost situation, how would we minimize that? And as you might imagine, we're going to use calculus to solve this problem. Now, just as in the prior problem and in any math problem where we're dealing with a geometric situation, let's draw a picture. And in this particular case, we're going to do a little more than that, right? Because we have to take into account the orientation of the farm, okay? So first, it's a rectangular farm, okay? So let's draw that rectangular farm like this, okay? And of course, we know that the sides are oriented with the cardinal directions. So that's just a fancy way of saying that they are parallel to the north, south, east, and west. Okay? Directions. Okay? And so let's let this side have a designation L to represent length, and let's say this side has a W to represent width. Okay. So first of all, we drew our figure. We drew it in such a way that the sides are parallel with the cardinal directions as stated in the problem. It's rectangular, also as stated in the problem. Now, obviously what we want to do is we want to find a function that we're going to minimize. What function are we going to minimize? We're going to minimize the cost. So let's write that here. So the cost function, which we're going to call C, is going to equal, now look at this here. The ones that are parallel with the north and south cost $5 per foot. So it'll be 5 times W for this one to fence that side, plus 5 times W to fence this side. Likewise, it costs $10 per foot to fence the ones that are parallel with the east and west. In other words, these ones here. So that'll be plus 10L plus 10L, like this. Now, of course, you can see 5W plus 5W is 10W. 10L plus 10L is 20L. So we get 10W plus 20L. Okay? That's our cost. Okay, now, so our cost, as we said earlier, is 10 times the width plus 20 times the length. But what else do they tell us in the problem? Let's look at it here. If the area of the plot, if the area of the farm is 144 square feet, what dimensions minimize the cost? So they tell us the area of the farm, the area of the plot is 144 square feet. Now this is a rectangle, right? There's no doubt about it. First of all, I drew it as a rectangle, and so therefore it's a rectangle. You see what I'm saying? No, I'm kidding. That was a joke. By the way, I should mention, now that I made that joke, whenever you're drawing a figure for your problem, try to draw it as accurately as possible with respect to the stated information in the problem. And if you're like taking a test on this material, and the reason why I'm like breaking out of my joke is I want to highlight, if you're going to take a test on the material, never ever trust the picture that is given to you if you are given a picture with the problem, because it might not be to scale. Instead of a rectangle, they might draw a square, So anyway, all joking aside, they told us it was a rectangle. I drew it as a rectangle. It is a rectangle. But when I made that joke, I realized that I wanted to remind you all that if you're ever going to take a test that deals with math and they give you a picture, only trust what is written about the picture, written on the picture, or written in the word problem regarding the picture. Anyway, now with that aside, let's continue back with this problem because that's so important, okay? Anyway, going back to this problem. They tell us that the area is 144 square feet, okay? So we remember that the area of a rectangle, okay, is going to be the length times the width. That's the area of a rectangle. In our particular case, we know that our area has to be 144 because they told us. So taking these two facts together, we see that the length times the width have to give us 144. And so I can either choose to express the length in terms of the width by dividing both sides by W, or I can choose to represent the width in terms of the length by dividing both sides by L. So alternatively, I could choose L equals 144 divided by W, or I could choose the width is equal to 144 divided by the length. Both of these are equivalent. We can use either one in the solving of our problem. Okay? So, and why are we doing this? Well, in order to solve this optimization problem, we're using the techniques of one variable calculus. We need to find a function in one variable. So it was necessary for us to be able to have the criteria of the cost so that we could find an expression of for the cost. But it was also necessary for there to be some underlying relationship between the two variables, the length and the width in this case, in order for us to be able to express one in terms of the other, as we have done here. So now, for us, I'm just going to use this one. Okay, I'm going to express everything in terms of W by replacing my L in my cost equation with this expression in terms of W. But if you want to, you can use this one in yours. And in fact, you know, obviously you're going to look at this example, you're going to see the way I do it, etc. You can redo it with the whole calculation we're about to do, but with this instead, make the adjustments necessary, and you can use that to verify for yourself that you would get the same answer. Okay, anyway, let's continue. So, as I mentioned, we're going to replace L in our cost equation with 144 over W. So let's do that here. So our cost is now going to be 10W plus 20 times, what is L? It's 144 divided by W. Like this. Okay. And so now you can see this is all in terms of W. And in fact, there's a 10 in front of a 10 here, and 20 is 2 times 10. So we'll be able to factor a 10 out to make it look easier for us. And in fact, now we can write it as a function of one variable. C of W is equal to 10 times W plus 2 times 144 divided by W. Okay? Okay. And so, and of course, let's just clean this up a little bit. I can multiply 2 times 144 to give me 288. So I can write my cost in terms of the width of my rectangular form as 10 times the W plus 288 over W. Okay? Okay. So this is our cost function now. Okay? Okay. So now we want to apply the first and second derivative tests on this function to determine what value of W will minimize the cost, if such a W exists. Always remember that whenever we want to do an optimization problem, it may or may not be the case that such an optimum, like a maximum or minimum, will exist or not. Okay. But so we want to use the first and second derivative test on this. Okay. And so if you recall, we need to first find the values in this case of W that will make the cost of W's that'll make the derivative of the cost 0. The C prime of W, we want to make that 0. We want to find out what W make that happen. Those W's will be known as our critical points. And then number 2, we want to know if the second derivative evaluated at those w's, at those critical points, are negative or positive, because if it's negative or positive, will determine whether we have a maximum or a minimum, right? Okay, so without further ado, let's calculate the derivative of the C of W. Okay. Okay. So the C prime of W is equal to 10 times the DDW of the W plus, let me just write it out like this first. I want to take the derivative of the 288 over W. And then flip right. So strictly speaking, here I kind of skipped a step. We know that if we have the derivative ddx, let's say, of a constant c times the function f, then the constant just comes out of the derivative with respect to x of that function f. So for example, that's why here, that 10, I just pulled it out, number one. And number two, inside here I had a sum of two functions, and I know that if I take the ddx, or whatever variable I'm differentiating with respect to, and I have some function like f plus g, then that'll be the dx of the f plus the ddx of the g. Okay, in other words, if I take the derivative of a sum of two functions, it'll be the sum of the derivatives. So here in the inside, when I take the derivative of this sum, it's the sum of the derivatives of the respective functions. And then over here, this 288 is a constant, and I'm going to reuse this here, and it's going to be 10 times the DDW. I'm going to simplify this in a moment. I don't want you guys to think that, I just want to make sure you guys see all these steps. Wait, let me see here. Okay, so then plus, I'm going to pull out the 288 here, and I'm going to have DDW of 1 over W. Okay. Now, the DDW of W is just 1, okay? Plus the 288. Now this gets interesting. What is this? Well, this is going to be negative 1 over W squared. Now let me explain why that's the case. So I know that the dx, let's say, of the function f divided by the function g by the quotient rule is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared here. Okay, whoops. And you guys might want to memorize it like that, verbally stating it in that sentence form. That comes from a first course in calculus by Serge Lang, which I used a long time ago. But if you look at most of the calculus textbooks, they'll have a variation of like a similar phrase. The bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And if you write it out as you say it out loud, it'll stick with you also like in the visual form, which can also help you to remember it, okay? And so look at this here. In this case, I want to show what the derivative was here. So it would be the dw of the 1 over W. Well, that'll be the bottom, which is W, times the derivative of the top, oops, here it's dw, of 1, minus the top, which is 1, times the derivative of the bottom, with respect to W, all over the bottom squared. And here, ddw of 1 is 0. Why? Because 1 is a constant. And then the ddw of W, that's just 1. So we end up with negative 1 times 1, which is negative 1 over the W squared. Okay? Okay. And so that's how I got this expression. Now let's clean it up a little bit. So 10 times 1 is 10. Okay? Plus, or in fact, in this case, we have a plus and this is a minus. So there's going to be a minus 10 times 288. That's 2880 divided by W squared. Okay? So now we know what our C prime of W is. Okay? The first derivative of our cost function with respect to W is this expression here. Okay? And we're going to now use this expression to find the critical points at which we will determine if, we'll determine if such points exist, number one. Number two, we'll use those points to determine whether we can in fact minimize the cost. Let's proceed. So we want to find the critical points. We want to find those W such that the C prime of W is equal to 0. Okay? So let's set this expression equal to 0. So 0 equals to 10 minus 2880 over W squared. Well, what I can do is I can add this to the other side to begin with. So plus 2880 over W squared plus 2880 over W squared. I can then start to simplify this. 2880 over W squared equals to 10. So what I can do is, on the left-hand side, I have 2880 being divided by W squared. So in order to let me say this. I'm going to multiply both sides by W squared, because by doing so, when I multiply the left-hand side by W squared, it'll cancel with this W squared. And when I multiply this side by W squared, in other words, this will be algebraically better. So this is gone. So we get 2880 equals to 10 W squared. Now here, I want to get the W by itself. So first, I'm going to divide both sides by by 10. So I'm going to get 10 here, 10 here. And I get W squared is equal to, and you can see here, it'll be 288, right? Because this is 288. This was 288 times 10 on top, divided by 10. We just get left with the 288. Okay. Now we're gonna square root this. So my W is gonna be the square root of 288. Now again, I want to say something important here. Usually, whenever I'm doing a square root, I will always affix a plus minus. Here, I did not affix a plus minus. And of course, the reason for that is we're choosing the positive square root of this because the W represents a width of a figure. Okay? But from an algebraic point of view, we would affix a plus minus there. In the physical context of the problem, we choose whether to pick the plus or the minus or both, depending on the kind of problem that we're dealing with. And again, of course, here it's length, so we pick the plus one. Now here, we want to get the square root. So we say, okay, 288, well, we know that's 2 times 144. And so if you want to, you could just say, aha, well then, David, that must be the square root of 2 times the square root of 144. And that's true. And if we do that, then we can see, aha, then this must be W equals to 12, because of the square root of 144 is 12, times the square root of 2. Okay? That is our critical point. The other critical point, as we said, there is another critical point when we take the W equals to negative square root of 288. But for our purposes, we omit that one because that one has no physical meaning in this problem. A rectangle of negative width doesn't mean anything. Okay? Okay. So we've now found the only critical point that matters to us with respect to this problem. So here I've drawn the conditions that we had learned earlier. This condition refers to a maximum, right? So if we have here, we can see here we're at the top of the hill, we're at the maximum. In this case, we can see that the derivative, the first derivative at that point A, at that x value A, is 0. Why? Because the tangent line is horizontal there. And moreover, the second derivative is negative. Why is that the case? Because if you imagine, look at the way your hand would go as it goes over that hill. Imagine, see how I'm imitating the shape of that hill with my hand? So I'm going from positive slopes to 0 slope, then to negative slopes. And if the f prime of x represents the slope at the points x, then you can see as the x is increasing, the f prime of x is going from positive to negative. That means the f prime of x is decreasing. That means that the second derivative is negative, okay? Because the f prime is decreasing. Likewise, right, you can see here in this other figure, which represents a minimum, that the f prime of a is again 0, right? Because we have a horizontal tangent there, right? But the f double prime is positive, because you can see as I trace out that minimum with my hand, I'm going from negative slope values to 0 to positive slope values. That means the f prime of x is going from negative values to positive values. That means the f prime is increasing. That means the f double prime is positive. Okay? Okay. Okay. So why did I remind you of these facts? Well, because let's recap where we are. We first got a function that represents the cost of fencing the rectangular farm for a given width W. We then found the derivative of the cost function with respect to W, so that we could find out what value of W makes the C prime of W 0, which is one of the two conditions necessary. The thing that remains for us is to determine whether this W is a minimum as we desire it to be. We want to minimize the cost of fencing this farm so that we can find the dimensions of the farm that minimize the cost, or whether this maximizes the cost, in which case, that's not what we want, and we'll have to basically just deal with the fencing problem in a different way. Okay? Basically, like, if this was the maximum, if we found that this value maximizes the cost, then, we would know not to use these dimensions, basically. Okay? Anyway, but let's proceed. Okay? Let's not lose the spring in our step, and let's hope that we've actually found a width that corresponds to the dimensions that will minimize the cost of this farm, so that we can tell Bob that we got a solution for you. Your farm has to be this size. Anyway, so let's proceed. So what do we have to do? We have to find the second derivative. So we can evaluate the second derivative at this value to see if we get, in fact, a positive or negative value at that point. Okay, so what is the second derivative? So the C double prime of W will be the ddw of this expression, 10 minus 2880 over W squared. Then, because of the basically the sum property for functions, this will be the ddw of 10 minus the ddw of this fraction, 2880 over W squared. Okay? Okay? And that's because, again, if we take the derivative, the ddx of a function minus another function, then that is just the ddx of the first function minus the ddx of the second function. Okay? Okay. When we take the derivative of a constant, that's 0. So this first term goes away. Boop, gone. Now we have this expression, minus ddw of 2880 over W squared. Okay? What's happening here? Well, again, we remember, this will be negative. I'm going to open up a bracket here. The bottom times the derivative of the top, so it'll be W squared times the ddw of the top, in this case 2880, minus the top, which is the 2880, times the derivative of the bottom, which is the ddw of the W squared, all over the bottom squared. In this case, W squared squared. And then close bracket. Okay, let me walk you through that again. So we're applying the quotient rule here because this is a fraction of functions. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom, which is the bottom, all divided by the bottom squared. Okay? I just copied this up here so we could have more room to do the calculation. So let's continue this calculation. So first of all, we see in this numerator the ddw of 2880. 2880 is just a constant, so this whole bit in the beginning just goes to 0 right off the bat. So let's do that. So this is minus, open bracket, The ddw of w squared, that's 2w. So it'll be negative 2880 times 2w divided by, and what is this? W to the fourth power. Right? Okay. So now, this is going to be positive. Negative times a negative is a positive. 2880 times 2. Okay, so that's going to be, let me do that here, because I don't have that much power to do it in my brain. 2 times 0 is 0. 2 times 8 is 16. I bring down the 6, carry the 1. 2 times 8 is 16 again, plus 1, that's 17. 2 times 2 is 4, plus 1 is 5. So we get a negative times a negative is a positive, as I said, so it'll be positive 5760. And then this w cancels out with 1 power of the w4 in the bottom, leaving us with w cubed in the bottom. Okay, so our second derivative of our cost function with respect to the width is 5760 over w cubed. So now what we're going to do is we're going to evaluate our our second derivative of the cost function with respect to w at our w. So our question is, what is c double prime of w c double prime of 12 square root of 2. So 5760 over w squared. In this case, this squared. I'm sorry, cubed. Whoops. Sorry about that. This cubed. Right? Okay. Right. Okay. So now here, I'm going to first cube the bottom. So if you know your rules of exponents, you know that if you have something like a, b, c, d, whatever, and you raise it to the nth power, then that nth power transfers to each term individually. So a to the n, b to the n, c to the n, d to the n. And in this case, the 3 will transfer to the 12, and the 3 will transfer to the square root of 2. So we're going to have 5760 divided by 12 cubed times the square root of 2 cubed. Now, let's start simplifying this little by little. First of all, in the previous step, we saw that the 5760 was actually 2880 times 2. So that's 2880 times 2. We just did that multiplication in the previous step, right? So that's how I know that one. I know that the 12 cubed is actually 12 times 12 times 12, or we can say 144 times 12. And the square root of 2 times 3 is actually going to be the square root of 2 times the square root of 2 times the square root of 2, right? Let me write that out for you here. And you can see here, this will become 2, and then I'm going to bring down my square root of 2 here. So I can write this as 2 square root of 2. And now look what happens here. First of all, I can get rid of this 2 with this 2 here. I can get rid of this 144 with the 2880, sort of, because the 2880 is 20 times 144. Because you can see 2 times 144 is 2 times 144 is 288, and then so of course if you multiply 144 by 20, you get the 2880. So this 2880 divided by 144 will be 20. Okay, so we're left with 20 divided by 12 times the square root of 2. Okay, and of course we can continue simplifying it. We can divide the top and bottom by 4. We get 5 over 3 square root of 2. Then we can rationalize it. Now a lot of students, what they'll do when they're rationalizing it is they'll multiply the top and bottom by 3 square root of 2. Right? But you don't have to. In this case, we just have to multiply the top and bottom by the square root of 2. And we'll get 5 square root of 2 on top. And the square root of 2 times the square root of 2 will be 2 times 3 will be 6. Okay? Okay. So let me point out something important here that's not really central to our discussion, but which I do want to bring to your attention, and that is, um, and that is, and that is the fact that I was able to simplify this by factoring it and multiplying it and using some facts that I knew, and that I didn't just try to brute force it. Now, I'm not saying you always can do this or that you always should do this, but sometimes if you see certain relationships among the numbers, or if you know certain relationships because of how you were calculating them, it's okay to exploit them to simplify your calculating procedure. So for example, we had seen when we were calculating the second derivative of the cost function that 5760 was 2880 times 2. So I knew that I could factor it like that. I also knew, of course, that the 12 cubed, I could have multiplied it all the way. I could have done the 12 times the 12, which was 144, times the 12 again, which would have been something bigger. And then this, I could have, well, that one I basically almost did do directly. Oh no, yeah, I did that one directly. But the reason why I was comfortable leaving the 12 cubed as 144 times 12 is because I knew that the 144 and the 2880 were related. How were they related? That the 2880 divided by 144 was 20 times that. So I was able to, so those kind of relationships came into view and enabled me to simplify the calculation. Anyway, so now before we let these little trees distract us from the forest, let us look at what we have done. Okay. We have found that the second derivative of the cost function evaluated at our critical point, w equals 12 square root of 2, gives us a positive value. So does it satisfy this criteria? The f prime of a is 0? Yes, that is satisfied. The f double prime of a is negative? No, that's not satisfied. So we know that we're not dealing with this case, which is a good thing because this is the maximum case. If that were true, then this width would correspond to a maximum cost. Now let's look at this criteria. Is the f prime of a in the terms of our setup over here? Is the f prime of a 0? Yes, we know that the c prime of w for this w is 0. Is the f double prime of a positive? Yes, right? We just saw that the c double prime at this value is positive. Strictly speaking, we could have just plugged it in here and realized that it was going to end up positive. We didn't have to simplify it all the way. But I just wanted to simplify it all the way because, I don't want you guys to lose the feel for calculating by hand. It's so important. But so anyway, so these two conditions are satisfied. So what we can now say for certain is that the cost of Bob's farm that encloses 144 square feet is minimized if the width of his farm is 12 square root of 2. So now the only thing that remains for us to do is to find out the dimensions of the farm. So we know our width is 12 square root of 2. And we remember earlier on that when we had drawn the rectangle, we had drawn it like this, where the W was this side and the lengths were this side. And we had concluded, because the area of the plot was 144, that the width times the length had been 144. And in particular, that, for example, the length was equal to 144 divided by W. Okay? And we were able to insert that for L in the cost expression to get our cost function, etc., etc. Now we know what width we need. We found it. This width corresponded to the width of the rectangle, of the rectangular plot that led to the minimum cost. So now we can plug in our value for W to get our L, our length. So 144 divided by 12 square root of 2. We can see here 144 divided by 12 is 12. So we end up with 12 divided by the square root of 2. I can rationalize this by multiplying the top and bottom by the square root of 2. And I can see that the square root of 2 times square root of 2 gives us a 2 on the bottom. And then on the top we're left with 12 square root of 2. You can see the 12 cancels with the 2 to give me a 6. So I have 6 square root of 2 as my length. Okay. Okay. So we can now state that we can now state the dimensions of the farm that minimize the cost. Okay. So we look at the farm, the rectangular farm. It must be the case that these sides, which are parallel to the east-west, are 6 square root of 2 in length, and that these sides that are parallel to the north-south axis are 12 square root of 2 feet in length, respectively. Okay, this will minimize the cost. Now, it didn't ask us in the problem to find out what that cost is, but we can find out that cost. We remember our cost function, our C of W, was let me see here, 10. Give me 1 second, please. $10W plus 20L, right? Let me see here. These are our W's. These are L's. Yes. Let me double check that, please. Yes. 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 And so now look at this. So now we can plug into our cost function. In fact, this is not CW anymore. Why? Because here we have the W and the L. When you take multivariable calculus, you can see that you could write this as C of W comma L because it's a function with 2 variables, the width and the length. Okay, but anyway, so we know that the cost will be 10W plus 20L. So 10 times W, so it'll be 10 times, our W is 12 square root of 2, plus 20 times our L, which is 6 square root of 2. And you can see that it's going to give us 120 square root of 2 plus 20 times 6, 6 times 2, that's 120 again. 120 square root of 2. And you can see that this is 240 square root of 2 because 120 plus 120 is 240. So 240 square root of 2. That's the cost. And that's the cost of fencing of Bob's farm. That was extra information that wasn't needed, but I wanted to show you what that was so that we could leave this problem totally solved. Okay. In any case, I hope you've enjoyed this example, and well, I hope to see you again soon. Thank you so much. You're still there? You're watching this video? Well, I hope you enjoyed it. In any case, if you did enjoy it, well, I encourage you to like it. Put that big thumbs up there. And don't hesitate and don't forget to subscribe to my channel. And anyway, and also add a comment if you want me to cover some particular topic. I can't make any promises. There's a huge list of topics I already want to cover, but time permitting, I may address that topic. And in any case, I hope you've enjoyed this video, and thank you again.